scientists get a glimpse of the entire inner structure of the planet.
Most of what we know about the Earth's deep interior has been derived from studies of earthquakes. Some of the deepest earthquakes occur quite deep, 700 kilometers deep. And the waves, just like throwing a rock into a pond of water, the earthquakes release energy, create waves. These waves travel all the way through the Earth. Through the center of the Earth, they're recorded on the other side of the world. And by studying these waves that have traveled, this is the job of seismologists, studying them around the world, we've learned that the interior of the Earth is layered. It's not just one single homogeneous mass, but it's comprised of layers of different compositions.
While earthquakes reveal a rough picture of the planet's interior, scientists often need more detailed information about the Earth's crust. One of their methods of getting it is through aeromagnetic surveys. The instruments in this specially designed plane detect the magnetic fields in crustal rocks.
Okay, warning and caution lights.
Check.
Okay, we're ready to start the engines anytime.
Okay.
Many rocks in the crust contain magnetic minerals such as magnetite. By analyzing the magnetic variations of these rocks, scientists can detect unseen geologic features buried deep in the Earth's crust. The plane flies low and slow over the terrain to collect data. Recently, an aeromagnetic survey was flown over North America's west coast. The objective? To explore the differences between continental and oceanic crust. As flight lines of data are pieced together on a map, an incredibly complex picture of the Earth's crust unfolds. Yet there is no hint of this complexity in the subdued terrain around Seattle, Washington, a major West Coast city. It is only through magnetic surveys and other geologic studies that the startling subterranean scene beneath the West Coast is revealed. Two crustal plates overlap each other below Seattle. One plate makes up the ocean floor, and where it meets the continent, it bends and dives underneath it. This is called a subduction zone. Sometimes the two plates lurch toward each other, unleashing a tremendous jolt at the surface. Good Friday, 1964. North America's strongest quake on record struck near Anchorage, Alaska, leveling the seaside city. So tremendous was the shock that it was felt in Florida, some 5,000 miles away. The Alaska quake was a subduction zone earthquake. Beneath the mountainous terrain around Anchorage, the Earth is restless. Here, the Pacific Ocean floor is subducting below the continent. The most powerful earthquakes on Earth are triggered by subduction of the Earth's crust. A subduction zone runs along North America's west coast, from Alaska, along the coast of Canada, all the way to Cape Mendocino in California. Subduction sculpts a beautiful, rugged coastline when it occurs at a continent's edge. This is because, over time, the subducting plate grinds forcefully on the plate above as it slides underneath. The top plate is shoved upward in response. Mountain ranges are built along the coast like the Olympic Range in Washington. After millions of years, the subducting plate sinks deep into the hot mantle where it begins to melt. Magma forms and sometimes rises through ruptures in the plate above. This creates another powerful force caused by subduction. Mount St. Helens in Washington erupted in May of 1980. Subduction triggered the eruption, which devastated the landscape for miles in all directions. A dense forest was blown over by the blast and buried under thick layers of volcanic ash. Mount St. Helens is one of many powerful volcanoes that were built by subduction along North America's west coast. Majestic Mount Rainier stands 50 miles from Seattle. Mount Baker, Washington rises near the U.S.-Canadian border. To the south, Crater Lake in Oregon was a huge volcanic peak before an eruption blew its top off 7,000 years ago. Many times in the geologic past, these volcanoes have erupted far more powerfully than Mount St. Helens. As long as subduction drives the crustal plates below, these sleeping giants will surely awaken again and again. The granite domes of Yosemite National Park in California mimic the shape of the volcanic peaks of the Pacific Northwest. Subduction created both, but the domes of Yosemite formed in a different way. Granite is a rock that owes its existence to subduction. It forms when a subducting plate melts and magma rises up through the overlying plate. But the magma often fails to make it to the surface in a volcanic eruption. Instead, it cools and hardens deep within the crust, forming granite. This is called a granite batholith. This is the process that formed Yosemite's granite. We see these rocks today because erosion stripped thousands of feet of earth off the top of the Sierra Nevada batholith. Another granite batholith was exposed by erosion in the state of Idaho. But geologists working in the area were puzzled to find rocks that were formed by subduction. Subduction generally occurs at the edge of a continent, but these rocks are 350 miles away from the nearest coastline to the west. How did they end up so far inland? Clues came from the rugged Hells Canyon area, just to the west of the Idaho batholith. On the banks of the Snake River, geologists found huge piles of volcanic rocks called pillow lavas. These rocks formed where molten lava poured into the ocean. Pillow lavas are forming today on the island of Hawaii. Lava is erupting from a small vent on the volcano Kilauea. From this fiery cauldron, molten fingers of lava flow in underground tunnels to the Pacific Ocean shoreline. Underwater, the lava seems to be fighting to stay molten, but it cools quickly, hardening into pillow-shaped rock. When they found these same kinds of rocks in Hells Canyon, geologists had a problem. A crucial ingredient in the rock's formation, the ocean, was missing. These rocks seemed wildly out of place. Further work in Hells Canyon yielded more rocks that had formed in the ocean.
And these rocks are really rich in them. There may be a fossil there. Hang on to that one. Here's another one.
Fossils of creatures that live on tropical coral reefs were found alongside the volcanic rocks.
We can measure.